you very much for the introduction and the invitation to be here. It's also nice to get a bit more interaction now with imaging community at EPFL, which I didn't have the chance yet. So yes, I'm going to talk about imaging using X-ray scattering contrast. I decided not only to go to my favorite topic, the tensor tomography, but start a bit also in 2D, explaining a bit the contrast modality and so on, and give also some examples there. So in general, me and my group, if it looks, yeah, how it goes. We work with X-ray scanning imaging techniques, which is basically what you can do with synchrotrons when you can have a very small and focused X-ray beam and then raster scan your sample for the beam. The big advantage of doing that compared to a full field imaging technique is that you manage to gather then in each point much more information. So in each point you can, I will just use that pointer here. So you can basically get spectroscopy information in each point or also scattering information in each point of your raster scanned image. So basically the working principle is illustrated here. Synchrotronmovies.com, by the way, a very nice web page to find whatever animations on synchrotron you can think of. But you can basically see you have a focused X-ray beam, you raster scan it over the sample, and in each point you record a spectra, and then the analysis of that spectra for certain points is translated into an image. So basically here are some examples on the whole range, what we are working in our group. So you have X-ray fluorescence that gives elemental contrast. Here is one example where we have looked at embryonic bone development in mice bone, and one can actually see here the calcification fronts in the bone, and one can see that basically in red you have the calcium, in green there is the zinc. So there is kind of like a zinc front in front of where the calcium happens. So XRF, elemental contrast. Then we have here one image where we looked with actually soft X-rays. So soft X-rays have then more interaction with lower elements. So we were working at the carbon edge. This allows to do then basically this STIXN, that stands for scanning transmission X-ray macroscopy, but then with near edge X-ray absorption contrast. So basically that is that you do a combined scanning, but also energy scan on the edge here, the carbon edge, and this gives then more chemical information. So here is basically the map of a cellulose fiber. So you see here scale bar is 1 micrometer, so quite high resolution. One can have easier, smaller beams with soft X-rays. So there we can go to like 30 nanometer beam size. In green here basically is a peak which is typical for cellulose. And then here on the yellow frame is basically this pre-peak here, which is specific for some binds which one finds in lignin. So with that one can actually then map objects which would have a very similar electron density contrast, also element-wise no difference, but one can get more the chemical information. But then what I will mainly talk about today is the scattering contrast. So here just one example of scanning VAX, wide-angle X-ray scattering, and scanning SAXS for small-angle X-ray scattering. We'll explain the color coding in a bit. So what we are interested in looking at and what these methods are mainly good for are hierarchical materials where you really have from the macro scale down to the nanoscale interesting features. So this is an example of bone, basically from the vertebra, or one can start with the skeleton, kind of meter scale. Then having a trabecular network, which is more kind of millimeter to micrometer, but then you have like cellulose, collagen, mineralized collagen, which are in the nanometer scale. You have the mineral platelets, which are very small. They are hard to detect just with very high resolution of electron microscopy, for example. But basically, you have really the span over the whole area. So for these hierarchical materials, either one can use different direct imaging methods, as kind of pointed out here in this scheme, for each of the length scales. Or what we do is kind of bridging the gap. That's also what was the title of the talk, basically by using indirect ways to probe still nanostructure. So this one is actually, again, an example of bone. Basically same volume, which is imaged here with a very high tomography technique, psychographic tomography, which we also do at basically the same beamline with coherent diffraction imaging technique. The resolution on the screen is not very good, but you still see kind of collagen bundles at least. And if we do this SAXS imaging technique, just also to keep in mind, it's really like a statistical technique in that sense that all the fibrils we have in the beam size, which here is basically beam size was 25 micrometer. This is a pillar of 25 micrometer, but then one gets still information on basically the main orientation, arrangement as such in this scale. So when we look at this SAXS patterns, I thought I put that in because maybe not all of you are familiar with small angle X-ray scattering. So what you can see directly is basically it's anisotropic. That's already good. We know we have some orientation in the collagen fibrils, but there are also more features one can see. In this direction indicated with the segments here, we have quite sharp peaks actually. Those one can be attributed to we call it the collagen peak, because it's basically from the collagen molecule along the fiber. There are gaps which are very much defined basically by the length of singular molecules of the collagen and kind of the triple helix, which is formed by them. And then they are filled with mineral platelets. And basically what we have then the electron density contrast from is between this organic collagen fibril and where we have really the mineral plate. So these are basically very well-defined distances here. So that corresponds to around 65 nanometer of spacing along the collagen fibril. In the other direction, the scattering is more kind of this fan-shaped pattern. If one looks then again into this basically scattering vector or scattering angle versus intensity curve, we can see that we have actually some bumps coming up. And that's what very often happens in small angle scattering, that you actually don't have very defined peaks, but more bumps and changes in slopes. Because also on the nanoscale, typically things are less organized compared to, let's say, the atomic scale of the crystalline planes, which you would probe in diffraction. So here, this first bump here is correlated to the diameter of the collagen fibrils. There is also more minerals basically around the diameter. So again, creating a contrast in the electron density. This one is much less defined in literature, depending also on species and location. That can vary between 50 and 200 nanometer. But even within a sample, you can already see the peak is much broader, so the distance is less well defined. So this is really a small angle X-ray scattering pattern of bone, which was recorded basically 7 meters away from the sample. So you really resolve the very small angles. One can, of course, also have the detector closer by. And this is now a combined picture. And I have maybe for people which are used to X-ray diffraction, it's a bit the unusual logarithmic scale, but I just wanted to show that SAXS and X-ray diffraction, or VAX, is the very same thing. You just probe different angles. So here in bone, we can actually see this shoulder we already saw an indication from is continuing. And this shoulder corresponds basically to the sizes of the mineral platelet thickness. So we can get information on the mineral platelet shape out of the shape of this scattering curve. And then in the really wide angles, you can see very sharp peaks appearing from basically the hydroxyapatite, which is the crystalline component of bone.
Marianne, just to understand what's causing this, obviously it's only Bragg's law that's being satisfied here, right? For the energy to be
basically the peaks, yes. I mean, you have then, I mean, Bragg law is just kind of relating the specific angle like to basically a distance, right?
Yeah.
But the shape of this one here is actually also correlated to the shape. So you have also a relation with basically the fractal dimension of a system. So in small angle scattering, if you have a slope in a double logarithmic plot of -1, that would be basically a long cylinder, because your dimension which changes is changing. Sorry?
It's the Hertz exponent.
I don't know that expression. We call it
fractal dimension.
Yes, it's the fractal dimension, exactly. So basically here what we can see is that we have a slope of about -2 at one point, which basically tells us that we have platelets.
Okay.
Right.
And this is all done at a single energy, is that right?
Yes.
Right.
Yes. Yes, we have a monochromatic beam typically in the for the scattering experiment. We work somewhere between 11 and 18 kV, somewhere like that. Yeah. Good. And then, I mean, that was kind of just to understand the single scattering point, but then for the SAXS imaging, the interesting thing is that we can really have basically a twofold resolution now. We can have the real space resolution, which is given by the X-ray beam and the step size, and then we probe basically over the reciprocal space the nanostructure. And both of them can basically individually be adjusted to the system one wants to probe, which length scales to probe. So we can basically vary the reciprocal space. We can go to small angle scattering, wide angle scattering for bigger or smaller structures. And the real space resolution, that depends then a lot on the beamline you use. So the SAXS beamline at PSI, we typically use beam sizes between 10 micrometer and 100 micrometer, but you can also go to a few hundred nanometer of beam if you go, for example, to ESRF, the synchrotron in Grenoble. That depends just basically on the beamline setting. However, there is a bit of a limitation to get a very small beam. At one point, you start then to have a very convergent beam, and with that, you would smear out the small angles in the scattering. So there is kind of a limit, but I would also say it makes sense to have not a too small beam, because in the end, if you would use a very small beam, you're better off with direct imaging. The main advantage of the technique is really to bridge between this like macroscopy scale and still getting nanostructure information. So just kind of a sneak peek into the beamline, how the setup typically looks like. We have a pretty spacious experimental table where one can also accommodate for some sample environment. One can also combine that with different in situ experiments, for example, and then basically just having a big flight tube, we call it, just a vacuum tube between basically the detector, which is here mounted in a 2 meter distance in the back. And you can also see we have directly linked also a wide angle X-ray detector, which then basically at the same time you can also get the wider angles. now we basically construct these images out of this SAXS imaging technique. One thing which we use a lot is these colorful plots, as we scientifically call them, where we have basically this HSV representation that the hue is corresponding to the scattering orientation according to the color wheel here. The saturation would be the degree of orientation. So basically, if we now take just one specific hue range and we look at the azimuthal variation, you can basically see how anisotropic this is. Normally, one can just, for example, one way of defining the degree of orientation would be just to have the asymmetric intensity divided by the symmetric intensity, and then the value in the HSV representation would be the isotropic scattering. So basically, black means there is no sample which scatters. So basically, if you see here, you take a blue point here that would correspond to a scattering pattern which looks like that. And to keep in mind the reciprocal space map, often you have the 90 degrees to your main scattering orientation is the nanostructure orientation. So this one here is a slide of trabecular bone, and you can actually see how nicely the collagen fibrils are following the macrostructure of the trabecular bone, kind of making this like rainbow effects around each lobe. This is, of course, not the only picture one can create. Basically, whatever analysis we do on each single SAXS curve, you can basically use as a contrast. Here, just a range of kind of very simple analysis, which here are now finally a non-bone example. So it's a more material science sample, and that is a composite material of carbon fibers in a polymer matrix peak. And what one can also see, for example, here is that one can even differentiate between orientations at different length scales. So we have the carbon fiber where we actually at this distance more capture X scattering. And we can look at the orientation of that, or we can specifically see where we have like a lamellar peak, lamellar spacing of the polymer, and then do this analysis in this Q range, and with that basically differentiate between different orientations at different length scales or coming from different structural elements.
Marianne, I have a question on the representation.
Yeah.
The material is 3D, and so its inherent orientation to 3D. But what you're showing here is the scattering angle as detected.
Yes, that is just the 2D projection of the real 3D orientation. For now. Wait for it. Yes. So just kind of one application example on that, and also then maybe what one can really analyze more is PhD student which just graduated at Chalmers. Adrian has worked in collaboration with the University Hospital in Zurich on some new material for bone scaffolds. So that is a material which you use if there is really a full piece of bone missing. So it's for this so-called critical sized bone defect. Basically, bone is very good in healing together. But if it goes above a certain threshold, and I think for humans that's about like 2 or 3 centimeters, the two bone stems don't find each other. So one has to find ways to basically guide the bone back together. So we looked at different scaffold materials which were made from electrospun microfibers with basically some mineral calcium phosphate nanoparticles in it. And we mainly also looked at scaffolds which had a random orientation of these spun fibers and aligned ones. And then they were implanted and basically 7 weeks after growing in the mice, taken out again. So this is just a standard CT we can do on these samples. One can see there is ingrowth kind of in both of the implants. Looks a bit better here. If we just look at basically the scattering intensity, we can also see there is quite a lot of materials in both of these scaffold materials. One can already see here that this one is kind of detached a bit. Now, if we look in the orientation plots, we actually see that here this one has a almost no orientation effect. So something is a bit off. So we also looked into more deeper analysis. So this is basically an analysis now more on this shoulder of the mineral platelets. The first one we did was basically just cross-checking, because for the assumption of calculating a T parameter, which is correlated to the mineral platelet thickness, one has to check that it actually follows that mathematical assumptions. And one of the assumptions is that the slope here, as was nicely the question before, should be basically -2 or smaller. And we found here that in this part, we have actually Gini exponents which are higher than, so the color scale is taken that 2, which would be really kind of a platelet, is gray, and everything higher appears red. So we can see that basically here there is some calcification happening. Electron density wise, there is no difference, but it is clearly not in the shape of good bone, let's say.
But it's still crystalline.
It's still crystalline, yes. And then also basically, if we do the full analysis, one can then basically get this T parameter, so the thickness of it. One can see that in this aligned scaffold, the bone grows in kind of a good quality bone, whereas here actually there is a different crystallization happening. Before I turn to 3D, I just want to also quickly mention that this is not only working for solid samples, we can also measure, we have, for example, done quite a lot of experiments where we do microfluidic together with this technique to map nanostructural in flow. One example is a so-called fluidic 4-roll mill. So that's a microfluidic equivalent of the old 4-roll mill, which is basically used to generate a lot of different flow patterns in the middle. Depending on how you have the velocities in the different channels, one can create very defined flow profiles, basically from a pure extensional flow to a rotational flow, and the shear, which is kind of 50-50 in between, if you go into more fluid dynamics. So basically we have this channel, and now we can also map again basically the orientation here of cellulose nanocrystals in flow. And we can also then with streamlines follow how a particle in kind of an extensional flow here is oriented. And this can basically be used or was used here by our collaborators to check some model prediction for fluid dynamics of kind of how the degree of orientation changes in an startup of an extensional flow. We can also not only look at kind of one orientation, but we can basically probe again different Q ranges. One here would be then more basically just probing one single particle, but then one can also look into a Q range where one starts to have basically interactions between particles. So now we studied in many different flow types, that is basically 10 million scattering patterns of different flow types. And one interesting thing we observed is if we actually compare the ratio of these two orientations, we have basically different populations depending on the interaction. So here we studied CNC, which had kind of a modification, which were repulsive. Whereas the CNF system had a lot of attractive interactions. So basically, the slope seems to tell us something about the interaction of the particle in the flow. So now moving on to 3D. So of course, it is interesting to study this three-dimensional object, also to get not only this 2D projection of an actual 3D orientation, but getting the full 3D information. Combining small angle scattering with computed tomography has been already done quite a while back. And basically then just doing in each Q range a separate standard tomography reconstruction. And with that here, basically that is just a dummy sample with 4 capillaries filled with different materials. One can see that one can spatially resolve all the scattering pattern. This was also done on brain. So in the neurons, you have the myelin sheets, which wrap around the neurons, and they have also a very specific distance of the thickness of basically these myelin sheets, which appear again as very distinct peaks in the scattering pattern. So just basically extracting these peaks, one can use that as a very selective contrast just for myelin in brain without any extra contrast agents. And this was already done in 2011. But assuming basically that the scattering contribution is isotropic. However, one could hope that neurons have some direction, and with that also the myelin sheets will have a direction. So here that's one case where this assumption is clearly violated. So what is the problem of why not having an isotropic scattering contrast? Basically, the one thing which is then heard is that if you do tomography and you look from the different projections, you always probe basically one voxel or subvolume where you want to reconstruct, your signal will actually change. And this is kind of against the standard assumption behind filtered back projection. So here, this is just an experimental proof of that, which is kind of clear if you think about it. This is just a thin bone slice and then measured from different angles with image registration, one specific point found, and then the scattering pattern plotted. And I mean, it makes sense if you think about it. The collagen fibers are oriented in a certain direction. If you turn it around, it will turn with, and the scattering orientation will, of course, turn. What you see in basically the intensity fluctuations is more related to the fact that this was done on a thin slice. And if you have it in a tilt angle, you have more material actually coming in. So that also means that we don't have enough information if we probe just one scattering axis. So if we just have one rotation axis, but we actually need to probe tilt angles of these rotation axes. So we need basically 2 rotation axes in the system to probe enough for our reconstructions. And then this was, as Michael was saying in introducing me, this I have worked on as postdoc when I was at PSI, and we were actually kind of collaborating, competing with another group at TU Munich, where Florian, the PhD student, was also working on a different reconstruction technique, and in the end they were published side by side. They are very different approaches actually. We worked with a system where we used basically a model in each voxel of the subvolume to basically model this 3D reciprocal space map. So basically the scattering in 3D, and then having an optimization problem for that. The approach from Florian was basically to go with the so-called rotational invariance. So basically it says that the scattering direction, which is parallel to your rotation axis, will not change. So this direction you can always reconstruct. And then he was introducing basically a sorting algorithm with virtual tomography axis to find basically in the 2D pattern, which would be the virtual tomography axis. And then that was reconstructed with 15,000 independent CT reconstructions. They have kind of stopped working on that, and this method has also been died. I think it's a very smart solution, and also it doesn't need any assumptions. However, what it suffers a lot from is basically that you have basically missing wedges already with a very big sample set. So there is not much room to improve that. So basically all the work we have been since then working on is still based on this principle of using as basically a model for the spherical harmonic, the model for the 3D reciprocal space map is a series of spherical harmonics. In our first study, we used basically only, and I never know if it's order degree or degree and order, but the zeros of one and the evens of the others. I'm a food scientist, you cannot ask me questions like that. But we used it basically, and then you have always the assumption of a cylindrical symmetry, right? You have basically a fiber symmetry. You can either have poles, equatorial poles, or a ring. And then in each voxel, we introduced basically a rotation matrix to change it into the orientation of the nanostructure. And reconstruct it basically in that way, kind of finding for each beam the path of voxels through it, and then having basically a cut on this spherical harmonics. For small angle scattering, that is just the big circle. If one goes to wide angle scattering, it's actually the cut with the Ewald sphere. And then basically having an optimization problem with basically the simulated intensity and all the measured data. From that, one of the advantages is that you get basically the orientation directly as one of the optimization or two of the optimization parameters out. And with that one can then get the nanostructure orientation. So that is how this looks like. In 3D, you have again this trabecular bone sample, and you can actually now see the cylinders represent the three-dimensional orientation. It's nicely following again the curvature of the trabecular bone. The color code here is degree of orientation. So what you can also see is that wherever there is a lot of curvature, the degree of orientation is higher, which also makes sense because there basically the mechanical forces would act in that way. So you have much more alignment, whereas kind of in the middle, where also the forces come from all directions, the degree of orientation is much lower. And we don't get only this orientation out. If we do that basically for all the scattering vectors or angles, we get the full 3D reciprocal space map out. So just for some numbers, this is was kind of a rather small sample. We recorded in total 830,000 scattering patterns, from which we extracted for each Q range. Basically, we reduced the data to just 16 points around the azimuthal angle, which gives then 13 million data points as input for the optimization problem, and basically in each voxel having 6 optimization parameters, so a total of 1.3 million optimization parameters, and then you would repeat that here 200 times for the bins in Q. Now, my PhD student Leonard has worked more on the project. I will actually first show this. We have seen that it's a quite ill-posed problem, and the optimization tends to get stuck in a lot of local minima. We had to use kind of a stepwise approach of having first coefficients fixed, then optimizing angles, and then fixing the angles, optimizing coefficients, and then basically letting everything free in the first step. What we notice is that we quite often came to what looked like 90 degrees of the orientation which we would like or which we would expect to see. Looking a bit more in detail, it seemed that like whenever the starting solution was kind of 90 degrees to the nanostructure orientation, it was kind of easier for the code to change basically from the ring to the cap, probably also related to the fact that we do have a missing wedge. We can only tilt to 45 degrees. So this was always a bit of a problem. We got a bit better control over it by introducing regularization terms, basically having a dot product between neighboring voxel as a regularization parameter. But then Leonard, in a next iteration, kind of threw away this orientation in each voxel part, and instead we are just using now the bigger base of the spherical harmonics, because the spherical harmonics are a complete base. So we, in the first approach, we thought we have less optimization parameters, so that should help. But a bit because of this double, I don't know, implementation of that, how you can actually produce maxima at certain distances, we seem to run a lot into problem on how the optimization was going. And you can see here the difference between kind of the old method and the implementation now. We also see that the whole optimization behaves much better. What is an additional advantage of this is also that we basically don't have anymore this assumption of one cylindrical symmetry in each voxel, which also means that now we can actually start to see multiple direction in voxels. So of course, as I showed in the beginning, it's basically a statistical average of a lot of collagen fibrils. So there is, especially here, if you have like domains where they start to cross, there is also different directions of the collagen fiber present. And by taking this assumption away, we can actually start to resolve them.
What are you showing on the middle graph? Is this like the spherical harmonics reconstruction of each voxel?
It's basically from one Q range. Yeah. And then now I'm not sure what he really plotted. I think it's still the spherical harmonic, because then, yes, this is still the spherical harmonic model. But then to get out the orientation, he's using Funk transform to get the kind of that you have 1 point direction. Just also kind of to say that we have improved also experimentally. The first measurement we took 36 hours, which is a bit long if you want to have, for example, biological sample with some statistical relevance measured. But we did already do now new measurements, also on other beamline, where we can actually get this measurement time still with the same sampling down by a lot. I also plotted, because I put the measurement time to get an overall estimation, because probably an hour per million voxel doesn't tell you much, but to compare between the different samples, it's basically this hour per million voxel, which is the relevant one. And you can see that we basically got it down from 96 hours to 6 hours already. And with kind of the upgrade of the synchrotrons, faster detectors, and so this starts to become actually realistic. Now I have one thing which I thought was also, which I have also discussed with Leonard a lot, and I thought maybe I can also get some extra inputs or ideas from this community. One thing is we struggle with is data visualization, because basically we have in each voxel this full 3D reciprocal space map. I mean, of course, I have already showed you a bit, like kind of, so we basically from this full, basically onion of 3D reciprocal space, we just take one shell, and then from the one shell, we just get basically the orientation out, and that is kind of the cylinder. So this is kind of one easy way, which often is enough. Here in this, again, trabecular bone sample, you can nicely see how it's orienting. We have now also started to try to work a bit with streamlines, as it's also done in MRI. And of course, one can get it into more artistic features, but maybe with less scientific content as well. One thing which is really like, even if you just take the arrow, like if you just have like this cylinder and you get to kind of high resolution, you don't see absolutely like nothing at all. If you maybe zoom in a bit and work around, you can get something, but here even kind of just looking at slices, there is not really too much interesting going on. And for this sample, these streamlines were extremely important, because here we could actually then see, I hope this video plays. No. Yeah, now. This is a piece from a narwhal tusk, so the unicorn of the sea. And it has this very nice macroscopic left-handed chiral. So this is a piece, just a millimeter piece out, to see if this macroscopic chirality is also reflected in the nanostructure. And if you look at just the vectors, you don't see anything. But if you do the streamlines, you can actually nicely see this kind of chiral turn, which is already present in just like kind of 1 millimeter of this 2 meter long tusk.